Well, friends, here is a happy Milo, and Milo is going to help us figure out how to do some questions with buoyancy. Okay, so here's Milo, and he has mass. In fact, he weighs 15 pounds, and pounds is our English unit, but we want to convert that into mass, the kilograms. And if we know that 1 pound equals 0.454 kilograms, it's a very easy conversion. Set up something along this line, and we find out that the pounds cancel out, and we figure out that Milo has a mass of 6.8 kilograms. Now Milo doesn't do a whole lot but eat and sleep, and he finds the bed, jumps on it, and settles in for a little nap. Now if you look at the pillow, or we should say the cushion here, you notice there's a little dimple where Milo is kind of pushing down, and that is his mass pushing down against the pillow, or against the mattress. And that is basically gravity pushing him down. Now you might recall that we talked about the difference between mass and weight is the idea of gravity acting on mass, but we don't really have to worry about that too much. Just worry that newtons is just a force, and it's pushing down, and in this case it's definitely gravity. But the fact that Milo is not floating away, or the fact that he's not dropping down farther, implies that he's in balance. So if there's 68 newtons down, or 6.8 kilograms of mass pushing down, there must be 68 newtons up, or 6.8 kilograms of mass going up, and that certainly is the case. Now, we did some of these in class where we had a little box, and if we have equal forces, one to the right, one to the left, it's not going anywhere, they cancel out. Or if up and down are equal, they cancel out. But if it's less on one side than the other, in this case, 40 newtons to the left and 60 newtons to the right, the net force would be 20 newtons to the right. And sure enough, what would happen in this situation is that it would shoot off to the right. And in the case of Milo again, he's not going anywhere, at least up or down, because they balance out each other. So let's see what happens if we can put Milo in some water, see what happens, because as you know, cats love water. So this is fresh water, so it's just plain old water, which has a density of 1. So we put Milo in, and lo and behold, he floats. Doesn't completely float, he's down a little bit, which implies, however, that he's less dense than water. And if you were to look at the forces acting on him, he's not going up, not going down, he's just kind of staying still. There'd be 6.8 kilograms of mass pushing down, or we could say 68 newtons of force pushing down, and back up is 68 newtons, kind of like when he's sitting on the bed. Now when he's on the bed kind of pushed back at 68 newtons, but now what's pushing back is this idea of force of buoyancy. And so the force of gravity down, force of buoyancy up, they're equal to each other, therefore he's floating and not going anywhere up and down. Remember that the force of buoyancy is this upward force that a fluid applies to an object, whether it be water, salt water, or we'll talk about even air can act like a fluid, like a hot air balloon, buoyant a balloon up. And that force is equal to the weight of the fluid displaced. So if I wanted to figure out how much fluid Milo is displacing, I could drop him into this big gravy boat kind of thing, and I'd force water out. So I do that, he goes down, and even though I don't have my animation, there'd be water coming down, which we could then collect. It'd be very similar to this, where I drop the ball in, and you see the water kind of dribbles out. And I could then collect that as the ball's floating and see what actual volume. So the water that kind of peed out here down on the deck railing here would be equal to the volume of that ball under the water. But the ball's not going anywhere. It's not going up or down. It's in balance. So here's Milo in the water. He's having a grand old time. And this is the water that kind of came out. And if we were to measure it accurately, we'd find that it's 6,800 milliliters. Or we could say 6.8 liters. They all mean the same thing. And if we know that the density of water is 1, which is 1 gram per cubic centimeter, which is the same way of saying 1 gram per milliliter, we can very quickly find out, without a whole lot of math here, if 1 gram is 1 milliliter, then 6,800 milliliters would be 6,800 grams, or 6.8 kilograms, or we could use that Newton stuff again. And sure enough, what we find here is that the force of buoyancy, based on the volume displaced, would have to be 6.8. 6.8 up, 6.8 down in terms of mass, or if we do the newtons, 68 newtons up, 68 newtons down. Another question we could kind of think about is, what is Milo's density based on all this? And we don't know what his volume is, but the way we could figure out his volume is we could just like push him down all the way in the water and see how much volume is displaced. So here's Milo out of the water. The water's up the top again. We know he floats, so we're going to have to kind of hold him down underwater. So here goes. We push him down, and again, I don't have an animation here, but the water would come shooting out of here. And when we collect it, it would be more than last time, because now he's completely underwater. And let's assume that it came out to be 8,500 milliliters, so that's the volume of Milo. We'll let him back out so he doesn't drown. So there's Milo's back out again. So here's a volume, 8,500 milliliters, or we could say it's 8,500 cubic centimeters. And we already know that his mass is 6,800 grams. And if we do the very simple calculation, density equals mass divided by volume, we find out that his density is 0.8 grams per cubic centimeter, less than 1, so therefore he floats. And so that's what it would look like. He'd kind of go down, come back up again, because he has a density less than 1. If he was greater than 1, then of course he would be dropping to the bottom. Of course, this is fresh water. If this had been alcohol, which is less dense than water, he might not have floated. He might have just dropped to the bottom. If this was salt water, he'd be even higher because it has a higher density. And the same amount of in the volume, since it has higher density, therefore the same amount of volume would have more weight to it, which would give a stronger support up. Again, that's why you float better in salt water. So Milo was a little upset when he saw a picture of himself. He said, wow, I'm getting a little heavy here. So he decided to go on a little exercise binge. And you can see that before his workouts, he was 6,800 grams. And then he kind of got lean and mean, sort of, and dropped 800 grams. And not only that, his volume kind of changed too. And so he got rid of that fat, which, by the way, is generally lighter than water. And he replaced it with lean, mean muscle. And now he's down to 5,500. So before he was 0.8, now he is 1.09. Now, of course, you can just look at this, and 6 over 8 is less than 1, and 6 over 5 is greater than 1, and now he has a density of 1.09. So now if we put him in water, I think you can predict what would happen. Having a density greater than 1, he would go down to the bottom, and he'd have to swim his way back up to the top. So what is the force of buoyancy acting on Milo? Is there any force of buoyancy? Well, a lot of people think no, there isn't, but yes, there is, because now he's displacing the entire volume of the body. And so it's 6,000 grams down, because that's his new weight, or I could say 6 kilograms or 60 newtons. But what's the force of buoyancy going up again? Remember, the force of buoyancy is equal to the weight of the water displaced. And so we have to figure out his volume. Well, we already have his volume because I gave it to you before. In that little table. So we know his volume is 5,500 milliliters. We know the density of water is 1. Therefore, if we rework our equation of density equals mass divided by volume, we know that mass is equal to volume times density. We plug it in. 5,500 times 1 is a pretty easy math. And we now know that his mass is 5,500 grams. So the mass of water displaced is 5,500 grams, which, of course, if we change that to a force in newtons, it'd be the force of buoyancy. So it's 5.5 kilograms, or if we talk about that force, it's 55 newtons. So now when we look at the comparisons here, it's 6 grams down, 6 kilograms down, and 5.5 kilograms up, or if we want to do in grams, but we'll go to this Newton thing. But in any case, they're not balanced. 60 is bigger than 55. 6,000 is bigger than 5,500. And of course, 5.5 is bigger than 6, assuming smaller than 6. I've got those backwards. But in any case, that would mean it's 6 down, 5 up. The net force would be actually 5 down, but it can't go any farther because now he's hit the bottom. And that pretty much sums up some of the things with buoyancy. Hopefully this will be helpful, and I'll give you some more practice problems for this kind of thing. So you can listen to it again if need be, and that might help you.